Hello everyone, I welcome you all in this class of soft computing technique. This is the second lecture of module 2. So till now we have covered module 1 and in module 2 we have covered scripts relations and examples, fuzzy relations and operations. Please see another example of fuzzy relation. So here we define two sets A and B. So we are defined two sets A and B. So A elements A, B, C, B elements U and V. So the relation RxY where we are writing as, so you know in the row we write A, B, C, in the column we write U and V. So the elements will be 0 to 1. So let this element is 0, 3, this element is 0, 6, this element you can write 0, this element you can write 0.5, this element you can write 1, this element you can write 0.4. So it is an example of fuzzy relations. So this can be written as so 0.3 by AU plus 0.6 by A comma V plus 0 B comma U plus 0.5 B comma V plus 1 C comma U plus 0.4 C comma V. Here this membership value 0.3 represents, this membership value 0.3 represent strength of the relation between A and U. So this is an example of fuzzy relations. Now relation of binary fuzzy relations in some element 1, 2, 3, 4. So in the column you may write 1, 2, 3, 4. So the relations are 0.7, 0, 0.30, that is 0, 0.7, 1, 0. You can write 0.9, 0, 0, 1, 0, 0, 0.8, 0.5. So the representation of a binary relation, first one we can represent the binary relation by membership matrix. So here the value represents the strength between suppose 0.67 represents the strength between 1 and 1. This 1 represents the strength between 2 and 3 and so on. So it can be represented in sagittal diagram. So just check it. So here the sets, let's set first one is A. So we are writing A. This is represent A whose values are 1, 2, 3, 4. So these are the values. Suppose set B. These values are 1, 2, 3, 4. So in the diagram we take the value 0.7. We can give the value as 0.3. Similarly that 2 and 3. So 2 with 2, 2 with 3. So you can write the value first one 2 with 2 is 0.7, 2 with 3, 2 with 3 is 1. Similarly 3 with 1 and 4. So 3 with 1 and 4. So with 1 relation is 0.9, with 4 that is 1. So with 3 and 4, with 3 the value is 0.8, with 4 0.5. So this is the sagittal diagram of the relations. You can say this is the representations of binary relation in the form of sagittal diagram. One is very simple diagram. So simple diagram, we can write the nodes like 1, 2, 3, 4. So 1 is related with 1, that is 0.7. 1 is related with 3, so that is 0.3. 2 is related to 2, 0.7. 2 with 3, 1. 2 with 3, 1. Then 3 with 1, 0.9. 3 with 4, that is 1. 4 with 3, that is 0.8. 4 with 4 is 0.5. So by this simple diagram, we can also represent a binary relation of fuzzy sets, or we can represent the binary fuzzy relation. We can represent binary fuzzy relation by using table also. So table, so here the value of the A, B and the value Rxy. So 1, 0.7, 1, 3, 0.3, 2, 0.7, 2, 3, 1, 3, 0.9, 3, 4, 4, 3, 0.8, 4, 0. Can be represented by these ways. Now we will try to understand the domain and range of a fuzzy relation. For this, we are writing a fuzzy relation in the form of membership matrix. So let's elements are x1, x2, x3, x4, x5. In the column, we are writing y1, y2, y3, y4, y5. So we will get a 5 cross 5 matrix. So 1 related with y1, the value is 0.9. So here value with y2, 1, rest we are assuming 0. Similarly here also 0, 0.4, 0, 0, 0. We are writing here 0, 0.5, 1, 0.2, 0, 0, 0, 1, 0, 0.3, 0.4, 0, 0, 0, 0.2, 0.6. So domain and range of a fuzzy relation R is also a fuzzy set, and the membership are defined as the mu domain R x, this is equal to the maximum where y belongs to the set, suppose B, mu R xy. So here we will get the membership value of each and every x. So we will take the maximum value of that row. So as for example, for x1, the maximum value is 1. For x2, the maximum value is 0.4. For x3, maximum value is 1. For x4, maximum value is 1. For x5, maximum value is 0.6. So this is the domain of R. Domain and range of a fuzzy relation R is also a fuzzy set, and the membership function is defined as mu domain of Rx is equal to maximum y belongs to B. Suppose this set we are writing as B, so here we are writing as A equal to the set x1, x2, x3, x4, x5, and we are writing that B equal to y1, y2, y3, y4, y5. So the domain of R is the membership functions mu of R is equal to maximum x belongs to A mu R xy. So here for y1 you will get 0.9, y2 is 1, y3 is 1, y4 is 0.3, y5 is 0.6. So here you can write these are the range of the relations. Now height of the relation is the largest membership grade obtained between any pair of xy. So you can height of R is equal to maximum x belongs to A, y belongs. So height of R can be written as maximum x belongs to A, maximum y belongs to B, Rxy. So in this relation, maximum value is 1 between the relation maximum value is 1 as the maximum value is obtained x1, y2, x3, y3, x4, 1, x4, y5 or. So the height of the relation is the largest membership grade obtained by any pair xy that belongs to the relation. You can write height of R is maximum x belongs to A, maximum y belongs to B, Rxy. That is the maximum value in the membership grade. So here you have seen the maximum value of the membership grade is 1. So here height of the relation is 1. So in this example, height of R is 1. It provides general procedure for extending Cripps domains of mathematical expressions to fuzzy domains. It generalizes point-to-point mapping of a function to a mapping between fuzzy sets. We are considering two sets A and B. So A is a fuzzy set on X. Fuzzy set on X. So A can be written as mu A x1 by x1 plus mu A x2 by x2 and so on, plus is mu A xn by xn. So we define the image of A. So the image of A. So the image of A under F is a fuzzy set B. So B equal to mu B y1 by y1 plus mu B y2 by y2 and so on, plus mu B yn by yn, where yi equal to f of xi, I equal to 1 to n, and f is a mapping from x to y. If f is a many to one mapping, if f is a many to one mapping, then mu by equal to maximum f inverse y, or you can write y equal to fx mu ax. So we'll take the maximum value. So try to understand this extension principle by one example. So here example is, so let a equal to 0.1 by minus 2 plus 0.4 by minus 1 plus 0.8 by 0 plus 0.9 by 1 plus 0.3 by 2. We are defining a function fx equal to x square minus 3. So here b will be b is 0.1 by minus 2. A for minus 2 is 4 minus 3, will get 1 0.4, you will get 1 minus 3. So you will get it as minus 2. 0.8, you will get minus 3. 0.9, you will get minus 2, and 0.3, you will get 1. So here that is also the minute one, so we will take the maximum value. So first to write minus 3, so there is only one value, so it is 0.8 by minus 3. Now for minus 2, need to take maximum value of 0.4 and 0.9, then plus maximum value of 0.1 and 0.3. So we'll get it 0.8 by minus 3 plus 0.9 by minus 2 plus 0.3 by 1. Now try to understand the general definition of fuzzy extension principle. So suppose F is a mapping n-dimensional product space x1 cross x2 cross x3 and so on cross single universe Y such that if x1, x2, xn equal to Y. So there is a fuzzy set AI on each xi. There is a fuzzy set AI on each xi. Each element in an input vector, each element in an input vector x1, x2, xn occurs simultaneously which implies AND operator. Means we will take the minimum value. The membership grade of fuzzy set B. The membership grade of fuzzy set B induced by the mapping F should be the maximum of the membership grade of fuzzy set AIs. The extension principle implies that the fuzzy set induced fuzzy set B induced by the mapping F is defined as defined as mu by equal to maximum x1, x2, xn equal to f inverse y minimum I mu ai xi if f inverse y is not equal to null set phi, 0 if f inverse y equal to phi. Here y equal to f of x1, x2, xn is a Krebs function. We will try to understand this concept with the help of fuzzy arithmetic and fuzzy numbers. Let I and j be two fuzzy numbers with I defined on x and j defined on y. Let the symbol star denotes a general arithmetic operation. So star is plus, minus, multiply, division. So an arithmetic operation So an arithmetic operation between these two fuzzy numbers denoted as I star j is a mapping to another universe of discourse, say Z, and by using the extension principle, we can I asterisk j x equal to the maximum x y equal to x asterisk y equal to z mu I x minimum mu j y. So take one example, addition. So we define two fuzzy numbers a. So we will try to understand this concept by addition of fuzzy numbers. So we are consider a fuzzy number a which denotes as approximately 1. So thus fuzzy set a can be written as 0.2 by 0 plus 1 by 1 plus 0.2 by 2. So we will try to find a plus a. So try to find a plus a. So a is 0.20, 1 by 1, 0.2 by 2 plus 0.2 by 0 plus 1 by 1 plus 0.2 by 2. So here is, and 0 plus 0 is 0. Similarly, minimum of 0.2 and 1 and 0 plus 1 is 1. Minimum of 0.2 and 0.2 and 0 plus 2 is 2 plus minimum of 1 and 0.2 by 1 plus minimum of 1 and 1 plus 1 is 2 plus minimum of 1 and 0.2, the minimum value is 1 and 1 plus 2 is 3 plus 0 point minimum of 0 plus 2 plus minimum of 0.21, 1 plus 2 is 3 plus minimum of 0.2, 0.2, 2 plus 2 is 4. So we can write it 0.2 by 0 plus 0.2 by 1 plus 0.2 by 2 plus 0.2 by 1 plus 1 by 2 plus 0.2 by 3 plus 0.2 by 2 plus 1, 0.2 by 3 plus 0.2 by 4. Now we need to write the maximum of these values. So the values are 0, so no one is maximum, so there is only one value of 0, so that should be 0.2 by 0 plus see, for the case of 1, maximum of 0.2 by 3, 0.2 by 4. So that is the addition of two fuzzy numbers. We are going to define a fuzzy number A, which is defined as approximately 2. So we can write A is equal to 0.6 by 1 plus 1 by 2 plus 0.8 by 3. B we can define as approximately 6. So B can be written as 0.8 by 5 plus 1 by 6 plus 0.7 by 7. So we will try to find A into B. A multiply B. So we are writing A as 0.6 by 1 plus 1 by 2 plus 0.8 by 3 multiply 0.8 by 5 plus 1 by 6 plus 0.7 by 7. So multiply 1 into 5 is 5, and here is minimum of 0.6, 0.8 plus 1 into 6 is 6, minimum of 0.6 and 1 plus 1 into 7 is 7, minimum of 0.6, 0.7 plus 1, 2 into 5 plus 2 into 5 is 10, minimum of 1, 0.8 plus 2 into 6 is 12, minimum of 1 and 1 plus 2 into 7 is 14 plus 2 into 7 is 14, minimum of 1, 0.7 plus 3 into 5 is 15, minimum of 0.8, 0.8 plus minimum of 0.8 and 1. This is 3 into 6 is 18, plus minimum. 0.873 into 7 is 21. So here we'll get the value of minimum. For 5, minimum is 0.6. For 6, minimum is 0.6. For 7, the minimum is, for 7, minimum value is 0.6. For 8, for 10, 0.8. For 12, it is 1. For 14, 0.7. And that is 0.8 by 15 plus 0.8 by 18 plus 0.7 by 21. So that is the fuzzy set. Now approximately 12. So this can be denoted as approximately 12. So in this class we have understood the different representations of fuzzy relations. We have understood domain, range and height of a fuzzy relations. Height of a fuzzy relation and extension principle. And general extension principle. So for today's question is, define a number a which is approximately 5 another number b which is approximately 7 so try to calculate a plus b, a multiply b. So these are the reference for today's class. Thank you.